evening, everybody. It's Thursday, March 19th, and this is Nighttime Mathematics Radio. Well, the shut-in continues, the homework continues, the classes have stopped. What's a math student to do? Well, the answer is come on in, listen to the program, tweet your math questions to us at Night Math Radio on Twitter. And when we get the questions, we'll try to answer them here live on the air. So, for the first few minutes here, let's take a break, listening to some of Apple's strangest loops, as always. And tweet the questions on in on Twitter. This is Nighttime Mathematics Radio. Welcome back, everybody. This is Nighttime Mathematics Radio, coming to you live from our secret headquarters by the bay, which we've been locked in for the last week, and we're getting a little punchy. For the moment, tweet your math questions in to @NightMathRadio on Twitter, and we'll try to answer them right here live on the air. And before we get some questions, we've had a lot of interesting mathematical nonsense show up over the last bit, which has been a lot of fun. There's nothing quite as much fun as a proof that just isn't right. So let's take a look at some proofs that are really, really, really wrong. Let's see if we can figure out what's wrong with them for that. So to start with, let's take a proof of something you know can't possibly be right. Been seeing a proof on the web that 2 plus 2 equals 5. And the proof goes like this. Pull out the trusty old notepad. Here's the notepad. It starts like this. It says, well, how do we prove this? Well, we know for a fact that 2 plus 2 equals 4. Learned that a long time ago. Well, so 2 plus 2 is equal to 4 minus 9 halves plus 9 halves. Because after all, you can always add and subtract the same number in an expression. Nothing wrong with that. Well, what's that equal to? Well, let's rewrite 4 minus 9 halves as the square root of 4 minus 9 halves squared. What could possibly be wrong with that? Plus 9 halves. Now, let's get fancy. Let's square that out. Just use FOIL. After all, there's two terms there, so we'll FOIL it out. That's the square root of 16 first. minus twice 4 9/2. That's the outer and the inner terms summed up. Plus 9/2 squared. Plus on the outside 9/2. Okay. That, now, let's simplify this out a little bit. That is 16 minus, well, what's this thing? This is, well, 2 times 4, which is 8, times 9 is 72, divided by 2 is 36, so 16 minus 36, plus 9/2 squared, we'll just leave in there for the moment, plus 9/2, still floating around on the outside. So how can we simplify this any? Well, 16 minus 36 is easy enough, that's just negative 20. Plus quantity 9/2 squared, plus 9/2. Well, let's rewrite this a little bit. Minus 20 is the square root of 25 minus 45. What could be wrong with that? 25 minus 45 is certainly minus 20. Plus the quantity 9/2 squared, still floating in there. Plus 9/2. So far, so good? Well, alrighty. We can rewrite this. That's quantity 5 squared minus 2 times 5 times 9/2. Right? 2 times 5 is 10. 90/2 is 45. Plus 9/2, quantity squared, plus 9/2. So this here must therefore be, this is a perfect square. This is the square root of 5 minus 9/2 squared plus 9/2. Oh, but that's great, because after all, 5 minus 9/2, the square root of 5 minus 9/2 squared must be 5 minus 9/2 plus 9/2. Cancels that, we get 5. So 2 plus 2 equals 5. That is a lovely bit of mathematical nonsense. And it is nonsense. You know this can't possibly be right, right? So the question comes up, where did they go wrong? How on earth did they end up with 2 plus 2 equal to 5? And the answer is something went wrong on the very second step. This step is false. But how can that be false? We just said something is equal to the square root of its square. How can that be wrong? Well, the answer is we know how to subtract 4 minus 9/2. What is 4 minus 9/2? You go back to your old fraction math. That's 8/2 minus 9/2. That's negative 1/2. And negative 1/2 is not equal to the square root of its square. You square negative 1/2, you get 1/4. You square root it, you get positive 1/2. So that line right there is actually false. That's something that isn't true. Notice that isn't a problem down here. And in fact, the cool thing is what they just did here, if you think about what that means, is they just, in this step, what they did is they took a minus 1/2 and replaced it with a plus 1/2. What does that do? That adds 1 to the right side. So that step right there is where the extra 1 came from. And it's really subtle. Now, this is silly, but people make this mistake all the time. And the reason is, people constantly write x is equal to the square root of x squared. And that just isn't true. But wait, you say, isn't the square root just the inverse function of the x squared function? No, it can't be. How do we know this? Well, let's look at what x squared looks like for a minute. Let me go over to my grapher. Now, let's remember what does f of x equals x squared look like in real life? This is a perfectly normal function. We know exactly what it looks like. That looks like this. Now, do you remember the test for something to be invertible? For a function to be invertible, it has to satisfy the horizontal line test. In other words, a given horizontal line must cross the function in exactly one point for a function to be invertible. And that's not true at all here. Let's take, for example, y equals 4. You can see where that, here's a y equal 4 line right there. You can see where it crosses. It crosses it there, and then I go over here. This function is absolutely not invertible. So, if it's not invertible, how do we have an inverse? And the answer is we cheat. Remember, we spent a ton of time when we were first looking at functions, talking about domains and ranges, and it was the most boring section of the math textbook. Because why are we talking about this? Domains and ranges are so obvious. This is the reason. We can cheat by changing the range. If the function f of x going from the real numbers to the real numbers is defined by x maps to x squared, that's not an invertible function. But if f of x, the function mapping from the non-negative real numbers to the real numbers, is given by x maps to x squared, that's a totally different function. It looks the same, it's got the same definition, but this function you're allowed to plug any real number into, and so therefore it doesn't satisfy the horizontal lines rule. But this function, you can only plug positive or zero into. You can't plug negative numbers into it. So that isn't this function that we're seeing right here. That's a totally different function. What that function looks like is this. Let me turn this one off, or actually add a new function here. New equation from template. We get a nice looking. Let's see. Can we get a? Oh, they don't have the template for this. Let's see. This is a piecewise defined function. Let me define it here. Oops, new equation. And I'm not. Let's see. I know there's a way to do this, and it's been a long time since I've done it, so I'm not sure I can remember how to do it now that I've done this. Let's see. This may be embarrassing if I can't remember it. It's not a vector field. It's not. This is a function that is defined it like this. It says y of x equals x squared. But what I can do here is I can just show it to you by shifting this thing over. Now we're just looking at this function. You notice I've hidden the negative numbers. That's because they don't exist anymore. Oops. Let me show the grapher. This is the function that we're now looking at. This is still f of x equals x squared, y equals x squared, you notice, but I've shifted the axis over so you can't see the negative numbers. That's because we're not allowed to plug them in. This function that we just typed, this function here, cannot take negative inputs. You said that. Its domain is only the positive and zero, is only the non-negative numbers. So in the grapher, that's all it is. That does satisfy the horizontal line test, and so this is invertible. And that's the function we invert to get the square root function. So this is invertible. It has nice inverse, f minus 1 of x from the positive real numbers, or non-negative real numbers, and actually again to the non-negative real numbers, is defined by x maps to x square root of x. Now, when you're writing steps in an equation, you can only really go from one step to another if you're allowed to use that step. If that step still makes sense for every possible x value that you're using, and this step doesn't make sense. In fact, this doesn't make sense for the only value you have. It's just flatly wrong. But this can be a lot more subtle if you're using x or some variable in there rather than just numbers. So this is a trap math students fall into all the time, which is they assume you can write that the square root of x squared is x, and it's not. Properly speaking, what the square root of x squared is something else. If we write square root of x squared, that does have a nice function we know about. That's the absolute value function, right? If it's a positive number, you get the number back. If it's 0, you get 0 back. And if it's a negative number, you get the same magnitude number but positive back. So the absolute value of minus 6 is equal to 6. Absolute value of minus 3 is equal to 3. So what does this all mean? It means you have to be very, very careful with square roots because they don't take every possible real number. So that was a lovely bit of nonsense that came in over the weekend. This is Nighttime Mathematics Radio. Let's take a minute or two to see if any questions come on Twitter. Back in a few minutes. Welcome back, everybody. This is Nighttime Mathematics Radio. Once again, if you have any questions, just tweet them on to Night Math Radio on Twitter. For the moment, we're covering mathematical nonsense, some stuff coming in over the last week. It's been a lot of fun. So what do I mean by mathematical nonsense? Well, what I mean is things that appear to make sense when you first write them down, but then when you think about them, they don't actually make any sense at all. And usually that's because the math is in some very subtle way wrong. But what do we mean by wrong? This is a much more subtle one than the last one. The last one was sort of obvious when you thought about it. This one's kind of cool. And the question came in that looks like this. I've been playing around with infinite series, and I know these are ones that aren't supposed to diverge. They aren't supposed to converge, but let's take a look at these. It said, let S be equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus ... And it turns out this is a famous series called a harmonic series. And it's a famous series because it turns out this one does not converge. This series grows larger eventually than any real number you might choose. This one goes off to infinity. I'm not going to prove that here. That's not what I'm interested in. What I'm interested in is somebody said this funny one saying, well, what happens if I subtract natural log of 2 from S? Well, I know what S looks like. The natural log of 2, I also know. Because that's got a nice alternating version of the harmonic series. It's 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. And then the student said, let's subtract one from the other. That'll give me S minus natural log of 2 is 1 minus 1 plus 1/2 plus 1/2 plus 1/3 minus 1/3 plus 1/4 plus 1/4 and so on. So that should be equal to twice 1/2 plus 1/4 plus 1/6 plus 1/8 plus ... which should be equal to, distributing that through, 1 plus 1/2 plus 1/3 plus 1/4 plus ... So how can this be? S minus natural log of 2 is equal to S? How can that make any sense? And the answer is nothing on this page makes any sense. Why is that? And the basic problem here is this. In writing these things down, and in particular in saying this is what we mean by S minus natural log of 2, we're treating an infinite series as if it were the same thing as an ordinary finite sum. And it really, really isn't. An infinite series doesn't actually make sense if you just think about it as, well, I add things up forever, because unfortunately you can't. See, and that's really different for any finite sum. I could write this sum out to, say, the millionth term and stop, and it would be a perfectly normal sum that would obey all the rules of summation. The sums would be commutative, they would be associative, everything would just work. But if I write that little ... at the end, I have to ask, what am I talking about? What do I mean by this? And it turns out what I mean by this only can make sense by using limits as defined in calculus. When I say I've got a sum of A0 plus A1 plus A2 plus A3 plus ... what I'm saying is, tell me what I want is the limit as n goes to infinity of A0 plus A1 plus ... plus AN. And the really cool thing is, that's the only way I can reason about it. The fact that I write it as if it were a sum does not mean that the usual rules of summation necessarily apply. I can't necessarily rearrange the terms, for example. I might be able to, but I have to prove that. And it turns out you can't always do that. And in fact, the harmonic series is almost the canonical example of a sum where you can't do that, where it's actually cheating to rearrange the terms. The same is true of this. It's cheating to rearrange the terms there. That's log, that limit of that is log 2 as long as you leave it in that order. But if you arrange the terms, it could be anything. So the very fundamental step to happen here, this turns out to be the nonsensical line. Thinking that you could take two infinite series, rearrange all the terms using apparently an infinite amount of commuting, then associating them infinitely like this because, well, they're just sums, isn't true. These aren't just sums. This is an infinite series. This is calculus. There's a reason it's later in the sequence. You have to prove things. And in this case, you can't. And that's where this all falls apart. This is Nighttime Mathematics Radio. Let's take a short break to take one last look at Twitter. If we get any questions in, we'll answer them there. And if not, we'll end the show. Well, it looks like Twitter is silent, the world is sleeping, the homework goes on, and we're all in our homes safe and sound. Tune in for another night's Night Math Radio tomorrow night at 9 p.m. and every weeknight till the current situation ends. For now, this is Nighttime Mathematics Radio, signing off. Good night, everybody.